Dobrze, to witam już wszystkich oficjalnie na kolejnym wykładzie z serii Zapytaj Fizyka. Będzie on po angielsku, także też zapowiem naszego gościa po angielsku. So our guest is Professor Sergei Gukov. He is a professor of physics and mathematics at Caltech, California Institute of Technology. He did his PhD at Princeton University, then he worked, among others, at Harvard, at Institute of Advanced Study in Princeton. Apart from being at Caltech, he is also working at Dublin Institute for Advanced Studies. He is also affiliated with Max Planck Institute for Mathematics in Germany. So, as you see, he's working just worldwide. And he used to work, and he's still working on mathematical physics, but in recent years he got interested in using artificial intelligence, in particular in mathematics and solving some mathematical problems. Maybe we will hear something about it today. So it's my pleasure to invite Sergei for the lecture, and the title is Mathematics as a Game.
Thank you, Piotr. Can you hear me well? Thank you. Those of you coming in, please feel free to come to forefront. This will be slightly more interactive. You'll get more fun if you're sitting in front, I promise you. So it's a pleasure to be here in Warsaw. I come here quite often. In fact, Piotr is a long-term friend and a collaborator, and his face will even appear on one of the slides. So, but the talk is going to be about interaction between mathematics and data science. And like I say, I'll try to make it a little bit more interactive, so I'll ask you lots of questions. So maybe just to practice, how many of you like mathematics? Please raise your hand. Okay, whoever didn't raise the hand, you're in the wrong talk. I'm joking. How many of you have some interaction with or some use of AI or machine learning? Can you raise your hand? Oh, very cool. So I have lots of experts. I have a good chance. Yeah. So if you didn't raise the hand in either one, don't worry, or in both. So this is supposed to be introduction, and hopefully if you're an expert, it will be somewhat entertaining, at least in some respect. My job is to give you gentle intro into some problems in mathematics and also some use of machine learning. So if you never worked with it, I'll try to introduce you to some of the, at least, basic concepts and see how they can work and how the two areas interact. So here on the slide, you see Ada. So Ada Lovelace, and she's actually quite famous for a number of reasons, so she's quite interesting. First of all, she's first and only a legitimate daughter of Lord Byron, famous poet. And she herself is actually a mathematician or a computer scientist. In those days, it was hard to attribute precise field, but she is sometimes credited with the first published algorithm. So as a result, and also she thought a lot about computer science and what we could call even artificial intelligence these days. So for example, this passage illustrates, so this is her writing, so this illustrates how she thought computers can think. And besides, of course, this was too early at the time, but she was basically trying to see if computers can be used for something other than calculations. So this is, you can view it as a precursor of AI. So there are many prizes named after her. Computer language Ada is named after her, and the list goes on and on. So I want to compare this to how we human think. So this whole talk is going to be, in some sense, based as a parallel between computer thinking versus human thinking. And in the next quote, I'll show you from Gregory Burns. So he's professor of neuroscience and economics in the US at Emory University. And he's studying how creative minds like Steve Jobs, Picasso, Warren Buffett, and others think. And this is his quote from the book Iconoclast. It's precisely about creativity. And here it sounds pretty negative. But what he really means by this is that we as humans, we have a lot of limitations and biases. So that's why it's very easy to trick our minds. And very recently, many Nobel Prizes, such as the one to Daniel Kahneman, for example, awarded for various biases and pitfalls of our thinking. So this, again, at this point may sound a little too harsh, but especially if it's taken completely out of context. But again, what he really means is that we fall in certain traps. For example, judges, when they, in a jury, when they make decision, they make more favorable decision after lunch than before lunch, and so on and so forth. So the list goes on, and this is clear statistics. Right, so as I promised, this talk is going to be interactive. Do you know who this person is? Okay, thank you. So you get the prize. So this is a dice, but it's a pillow, so it's soft. I'll try to throw it. Good job. This is Richard Feynman. I come from Caltech. And by the way, just like with machine learning, there will be rewards for various actions. Yeah, I come from Caltech, and we love Richard Feynman. And this is one of his quotes. So I'll give you a couple of quotes before we get to more serious business. And he describes scientific process of discovering, in fact, in theoretical physics, fundamental laws of nature as watching the gods play the game of chess, but in a situation where we see pieces moving on the board, but we don't know the rules. And our job is to figure out what the rules are. This is actually quite accurate. As many scientists can vouch, this is very close to what the scientific process is. So now, again, think about the parallel between how we human think and how we human learn and how machines learn. Machine learning is actually very close. By observing certain instances number of times, machines infer certain patterns and laws and draw conclusions. So this is very parallel. And when I came to the subject, that was around 2015, with the hype of AlphaGo and other exciting developments, I was not a computer scientist by far. And my question was, let me spend 1 month of my life analyzing what's happening here, and I hope that I don't need to learn the subject. So all this hype of AI will just pass. It's not going to touch pure subjects such as mathematics or theoretical physics, because we love theorems. We love paper and pencil. I mean, it could be useful for areas where there is a lot of data, maybe astronomy or particle colliders. So there you need to analyze something, or biology. But in a pure thought, if you play Math Olympiad games or solve puzzles, how could it be helpful? I mean, I didn't think that AI would be useful for that. So, of course, the fact that I'm standing here in front of you and presenting this is because I proved myself wrong. Unfortunately, I couldn't justify that I don't need to learn it. In fact, what I convinced myself of is that it's a very useful tool. It's like a pocket calculator of the future, so it's useful to have it. I mean, we may not use it, but if we do, we're going to be in advantage. So that's basically what I learned in these years, and that's what I'll try to illustrate with a couple of examples in this talk and describe challenges in going forward with this direction. Okay, do you know who this person is? Kasparov. So who said it? Oh, okay. You also get a prize. I'm told this is a bag, so it's a dice, but it's also a bag. It's a dice because when computers start learning, they first make random steps. And as human, we also make random steps at first, but then we improve and so on. So that's why I distribute dice as most of my prizes, not all of them. So yeah, this is Garry Kasparov, and I was very fortunate when I was a kid to go to his chess club. And that was in late 80s. And what surprised me back at the time, because I've never seen computer anywhere else, this was actually my first encounter with computers. This picture is a little later, but my encounter with him was in late 80s. So he encouraged us to play not only against each other as kids, but also with a computer. And yeah, so here you can see he is smiling, and probably there is something good about his pedagogical technique of teaching us how to play chess. But a few years later, so this is his, I think, first match with Deep Blue. So this is IBM's machine, which is not quite AI system, but it has many different pieces. And in the next year, 97, he famously lost. So computers basically outperform human in chess at that point. And now we also know that in games like Go, and basically there are no board games left for us to be better than computers. So let's think a little bit about this and how grandmasters like Garry Kasparov learn and play chess. So if you're new to chess, showing a board like this probably reveals nothing. But if you play chess well, in fact, if you're at roughly his level, then of course you immediately see what's happening here, who has stronger position, what this is. In fact, this is a famous chessboard. I don't know if anybody knows what it is. No? No, that's not the one. Okay, this is a very hard question, so no prizes for this. But the point is, once you play many, many games, when you become familiar with whatever problem you're trying to explore, showing a picture immediately reveals a lot, and you pay attention to many parts of it. Global details, local details, everything, you process this very quickly. And there is a parallel, again, between how we humans learn and how machines learn. Machines also see many, many instances of the same problem or similar problems. They infer generalizations, and that's how they learn. So there is a priori nothing wrong with that. So therefore, without further ado, why don't I take this kind of strategy and apply it to mathematical problems? So in today's lecture, I'll talk about, I promise to teach you a little bit of mathematics. So this is going to be a very simple mathematical problem in which we try to decide whether entangled string is knotted or not knotted. So these are headphones that I got at MediaMarkt earlier today. So they're pretty cheap and simple. So they can be tangled, and we all know how hard it is to untangle headphones. So it's from previous struggles. I decided to use this as an example. And mathematicians call this unknotted string where endpoints are attached. I don't have glue, but imagine that I'm gluing this in a circle. They would call this unknot because there are no knots inside. So now, if I do this, if I take it, produce some kind of knot, and also tie the endpoints, so I create what mathematicians would call a knot. So here is the result of it. Ta-da. So it actually has two knots. One knot is tying my ends here, but this is simply because I don't have glue and I want to attach them together. But then there is also something happening, some entanglement happening here in the middle. And the point of mathematicians who study this is that there is no way you can get rid of it without tearing apart my headphones. So no matter what I try, I can be very clever, sophisticated, but I cannot get rid of this. And this entanglement structure they call knottedness. So therefore, natural question for those mathematicians becomes to classify or understand when such a thing is knotted or when can you disentangle it. It sounds like a very simple question, and that's why I decided to use it as my main example throughout this talk. But as I show you in the very end, it actually has connections to very deep mathematics. Connections for kind of problems where you can win $1 million if you solve the problem. So everybody in mathematical world thinks that they're useful. By the way, I ruined my headset, so you can say that in this lecture, one sort of headsets was destroyed. So going a little forward, I want to point out that this kind of entanglement is very similar to child's game. So I also purchased earlier today a couple of books. So these are various games for our children to navigate this labyrinth. And as you can see, the entanglement patterns are very similar, so between what mathematicians call knottedness and the games. So you already can anticipate what's going to happen next in the rest of the talk when we'll be comparing math problems to games. Anyway, coming back to this question, so this is, for example, such a tangled configuration showing here on the screen. And it has 10 crossings. It's useful to sometimes keep track of complexity of what you see. I'll explain in a second why this is useful. This one has 10 places where the string crosses either over or under. And natural question is, can you, without tearing it apart, transform it to something which is completely unknotted? So how many of you think that, yes, you can transform it to something unknotted? Please raise your hand. Okay, some of you. How many of you think that you cannot transform it into something unknotted? Okay, this is tough audience. Yes, that's a correct answer. So this is non-trivially knotted string. That's very good. So how about this one? So who thinks that this is unknotted? Raise your hand, please. How many of you think that this is knotted? Raise your hand, please. Okay, kind of maybe close. How many of you prefer not to make a decision, that this is just too complicated? Okay, vast majority. So that probably is the right answer, because it illustrates that the more complex it gets, for example, now with this 30 crossings, it's much harder to decide. And our initial training, even for experts, is not sufficient to process this very quickly. And what I'll try to explain later is that problems like this do touch upon very serious problems in mathematics, but they require processing, analyzing this data when you have not just 30 crossings, but 100 crossings. And then things get really busy. So they get as busy as this diagram here, probably. Anyway, to give you the answer, this is actually unknotted. So all these 30 crossings can evaporate without tearing the string. So we can just undo it, and that's it. All right, so can we formulate this problem as a game? I mean, trying to decide whether it's knotted or unknotted as a game of chess of some sort. So maybe one last fact from mathematics of this is that a long time ago, Kurt Rademeister proved that in order to relate such complicated-looking diagrams to unknots, if it's ever possible, you only have to use 3 moves. So in chess, you have many moves. You can move the rook, you can move different pieces in different ways. Here, Kurt Rademeister showed that this kind of game requires only 3 moves. And these are the ones which either eliminate crossing or change the type of crossing, something like that. So in some sense, this is very boring, because it reminds us of a very simple Atari game where you can just move joystick left, right, or forward. So there are 3 moves. That's all you can do. In fact, complexity of this game is somewhat similar, as I'll try to show you. And another interesting remark, curious feature of machine learning community is that people who do AI, they love to play games, especially a branch called reinforcement learning that I'll be telling you about. So this picture of several Atari screens is actually taken from a very influential paper of DeepMind about 10 years ago. They proposed very interesting AI algorithm, which up to present day is still considered as pretty good and is quite widely used. So before I leave the world of knots, so actually I explained already a piece of mathematics, so I promised to leave you with some social residue of facts from math, from data science, and maybe even some rewards. So this is yet another social residue. So if you like this kind of games or want to try yourself on something else, I kindly ask Piotr to help me distribute these handouts. So this handout is produced by one of my former students, Angus Gruen, and it actually has 4 copies of the same thing in 2 rows. So in fact, the knotted strings in the first row are exactly the same as the ones on the bottom, and your job is to identify which one is which. So as you can see, they don't have too many crossings, but it's a slightly non-trivial game. So if you're bored with what I'm describing, in the meantime, you can play with this, or if you bring it home, please show it to your family members over the dinner and see how fast they can solve it. Yes? Oh, this is this paper where so this is actually the bottom of the slide is figure 1 of the paper that introduced DQN algorithm, DQN. So this is deep network version of Q-learning. So Q-learning is a famous classical algorithm, and this is deep network version of this. So I think you definitely should get a prize. So how about this one? So this is a very good question. I also want to encourage questions. So this is a reward. Okay, So this is, I'm not going to ask what this is. Actually, it goes back to 1971. It's one of the first computer AI systems which is meant to interact with human and reason. So this is going to be now change of gears, change of topics. I told you a little bit about mathematics, and it sounds like simple knotted things. So this is going to be now computer science or data science part of the talk. And I always, when I gave this talk in previous years, like I said, I started working on this in around 2015. So around 18, 19, I always have to apologize that this part of the talk belongs to a very specific branch of computer science, which is called natural language processing or natural language understanding. The goal of that field is, as name suggests, to understand how computers can process language or understand language. So this system, which could be described as one of the first AI systems, was designed in 1971. And as you can see, it's pretty decent. Computer is answering questions that a person asking. It's not quite as good as ChatGPT because conversation only is about basic shapes in the box, so universe of things that it can describe as finite, but it's pretty decent. It was invented by this person, Terry Winograd. Back then he was at MIT, and he's considered one of the founding fathers of this subject of natural language processing, natural language understanding. In fact, he has several books. One of them is this famous book on cognition. And yeah, so Terry is famous for many different things. Oh, by the way, this name on top is the name of this AI system. So extra credit question is to figure out what the origin of this name, what it means or where it came from. Anyway, fast forward, Terry, in later part of his life, moved to Stanford. He had many good accomplishments and also many successful students. So this is actually one of his students. Can you recognize who he is? Yeah, who said Larry Page? Okay, very good. This is actually a much harder question, so you get a much bigger one. Okay. Yeah, so this student of Terry Winograd at Stanford is well known for Page algorithm named after Larry Page. Well, that's his last name, but people joke that it's also searching through pages, and so it's, of course, so relevant to his future. So Larry Page became the CEO of Google, or co-CEO, and according to Forbes, is 13th wealthiest person in the world. So Google will play some role in our talk. I'll come back to Google's DeepMind and other things, but let's move on. So speaking of jokes aside, of more serious things, so one of the things that Terry Winograd introduced even back in those days when we didn't have powerful computers is what we now call Winograd schemas. These are supposed to be hard cases for computer so we can make a decision whether it's processing information correctly or not. So basically kind of stress examples, stress cases. And these are, imagine that you have to either parse the sentence or translate it to a different language. And these are what we call Winograd schemas, are supposed to illustrate whether the computer really understood what's going on. Because sometimes when you translate, you have to put the right articles depending on which words play in what role, or depending on gender, you may use different choices. So he devised these cases where it's really important to understand what's happening. And let me just go through one Winograd schema. For example, the trophy would not fit in the brown suitcase because it was too big. So if I ask you what was too big, you would immediately answer the trophy because that didn't fit in the suitcase. But there are several potential choices here. And if I change my question to what was too small, you would quickly change your answer to say that it was suitcase that was too small because that didn't fit the trophy. So therefore, if you're trying to translate this English sentence in some other language or parse it or understand as a bigger chunk of text, we have to really understand which word is playing what role. So this kind of non-trivial sentences, there is another one on the screen, or this interesting Vinograd schemas. I'll come to them a bit later. So these are supposed to be slightly harder cases for translation. So brief history of machine translation in this field is that it was basically statistical in late 90s and early 2000s. And this is basically shown by, in fact, there are two versions here, phrase-based and syntax-based. SMT stands for statistical machine translation. These are red and blue lines. As you can see, the progress is slow over years, and this indicates quality of translation over time. So on the horizontal axis, I have years. On the vertical axis, this is so-called blue score. This is bilingual evaluation under study, which is traditionally the score used for quality of translation. Just as a reference, a good translator would probably do 30, 40. So as you can see, performance at the time was maybe still subpar to human. Anyway, my point is that it was statistical in the way it worked. So let me tell you a little bit about what's under the hood. Statistical machine translation basically consisted of two systems. One, which is taking original text in an original language that you want to present it with, trying to process it and spit out a vector, which is being fed in the second part, so-called language model. So the first was translation model, second is language model. And the job of the second one is to take this probabilities or distribution and produce the text in a new language. So both parts functioned on probabilities. That's why it's called statistical. So something that we see here is around 2015, 2016, a different world of neural machine translation is overtaking at much faster speed. And basically, that's what happened. So that was one of the major developments around that time. So hopefully with this talk, I'll be able to explain why we live now in the world we are and what exactly happened around, say, 2015 from the viewpoint of this branch NLP or NLU. So in neural machine translation, the basic algorithms and architectures were quite similar. So this architecture is called seq-to-seq. I'll also give you some small intro into how machine learning works. So the simplest one or most relevant one here is seq-to-seq is based on several units which take input data recurrently one at a time from your sentence or chunk of text, produce another vector in a big multidimensional space, feed it to the second part. So these two parts which are called encoder and decoder, they're kind of analogous to this language model and translation model in statistical machine translation that I mentioned. And the second component now spits out a sentence using this recurrent neural networks or something similar. Other units, LSTM units, for example, produces a sentence in a new language. Or if you want to parse text, it produces whatever input you want. So because there are two components and it's very sequential, the name is sequence-to-sequence or seq-to-seq for short. As you can see, it's not ideal because in this example, which is actual example, the input sentence is English sentence. You asked us to call you back after last Friday. And German translation that came out is Wir hoffen jedoch, dass Sie bei Ihrer Reiseplanung weiterhilft. So the translated sentence has no word Friday. And if I translate it back to English as best as I can, it will probably say something like, we hope, however, that we'll be able to help you with your travel plans. You can see how in machine translation this could happen, that somehow in this big representation space, these two sentences ended up close enough that machine got confused. But it's clearly not ideal. It's clearly hallucinating something. It's not perfect, and yeah, there is room for improvement. You have a question?
Essentially, like we compare interpreting it and then recompiling it. Is that what we're doing?
Well, we are encoding first input into multidimensional representation space or something similar, and then taking just vector in that space and decoding it back using a different system.
I just want to stress that it's basically not a text-to-text function, but rather text to some abstract.
Exactly. Yeah, definitely. And each step of both components is done, you could say, stochastically, because it uses neural nets or whatever it learned in the training process. So it's not ideal. And yeah, so here are some more examples. This is from around 2015, 2016, when things were not quite perfect. So you can see what's happening here. If you do happen to speak any of these languages, probably you have more insight why this actually happened. So these are some funny translations back from those days. Okay, let's see. I still have 1 or 2 prizes left, so maybe I'll ask yet another question. Do you know how many of you use something like GPT? Can you raise your hand, please? Okay, can someone tell me what GPT stands for? Okay, so you already got it? Well, you also have it. Did somebody say who didn't get the prize yet? Going once, going twice. Oh, okay, someone on the very top. So can we please pass it up? I'm not going to run or try to throw. That's way too far. Thank you. Yeah, so T in GPT stands for transformer. So let me come back to this in a second, and that's going to be the key. So something had happened around 2016. In fact, Google quickly switched Google's translation from this previous models to this model based on attention mechanism, and use neural machine translation ever since. So statistical machine translation is now far in the back. And this mechanism called attention actually came from computer vision originally, but then was quickly adopted in this area and in fact in many other areas. And what it did, it actually helped to a situation in the previous slide. So here, the issue often is that sometimes, it's basically hard to keep context over longer chunks of text. And there are several problems here compounding. So first of all, yeah, keep this context is hard. Secondly, if your length of translation is large, then passing this through many layers and many activation functions, those of you who know what I'm talking about will immediately realize that this leads to problems of vanishing or exploding gradients. So that's another problem with, again, longer chunks of text. And of course, there are other things such as hallucination, making up information, and so on. So all of these problems, or many of them, maybe I shouldn't exaggerate, are reasonably well solved with this attention mechanism, which basically tries to keep context information as part of the translation. So usually this is encoded in what we call attention metrics, which basically tells us what are the correlations between sentence and itself, or maybe sentence and its other translation. So here, for example, are illustrations of both. So this heat map kind of shows how different parts are correlated with either itself or different translation. And here, for instance, you can see on the right the sentence, the animal didn't cross the street because it was too tired. So if I ask you what does it represent or stands for, so who was too tired, either animal or street, these are both nouns. But of course, it's the animal who was tired, and you can see that this higher heat map response indicates that, yes, that's what machine learned, basically. So this is how it learns, and this attention mechanism became very useful. But then another influential paper, also involving Google, that I already mentioned earlier, basically said the following. It said, throw the rest of your architecture and just keep this piece as a main centerpiece. So that's what the title of the paper suggests. And this architecture became known as transformer. So that's what's inside your ChatGPT if you use this. Okay, so this was, as you can see, 2017. attention all you need, and this is transformer architecture. This is T in ChatGPT. It's pretty complicated. It uses very interesting versions of Fourier transforms and other tricks, but all in all, it's mostly based on this attention metrics, which can keep the context, and that's I guess, big part of the success of many engines and systems in present day as far as translation goes, or parsing the text. So this is a slide from one of presentations by Lukasz Kaiser. So at that time, he was in Google. Now he left and joined OpenAI. I encourage you to take a look at his presentations, which are a lot of fun. And for instance, back then in 2017, he makes a comparison of how previous version of Google Translate compared to Transformer, which at that point was not implemented yet anywhere. And of course, you see more green on the right side. And again, we see our friends, Vinograd schemas, which are these interesting sentences where you have to really know the meaning to translate them properly. For example, the cow ate the hay because it was delicious. If I ask you what was delicious in the sentence, of course, some of us may think that the cow is delicious, but the proper answer based on grammar is that the hay was delicious. Yeah, that's being translated into French. Yeah.
By saying agent systems, did you mean single agent systems or multi-agent systems? You said something about agent systems.
Well, I said AI model, so this can be implemented in many different ways. Usually, of course, we have multi-agents, yes. Yeah. But it depends, it actually varies. All right, so this is to illustrate that the generative part, so GPT has this generative component, that's the G, and that's another cool thing that I like a lot about this Lukasz Kaiser's presentation. For instance, he illustrates that at that point he was trying to argue, again, when transformers were not popular, this was like a branch, not really dominant branch. Now it's very popular, but like I say, back in the day I had to apologize that I'm talking just about one particular chunk of machine learning, and now of course this is the main chunk, or most popular one. Anyway, so Lukasz here illustrates that it has a really good generative skills. For instance, here Transformer is asked to create a Wikipedia article, and it's given only one word at the beginning, the transformer itself. So transformer is the beginning, and it completes the rest of the sequence to make it like a Wikipedia article. So you can see that in 2017, it already performs what ChatGPT can do for you. So basically, you can see why it evolved and why ChatGPT was inevitable, basically. That already in this 2017 talk, you put on a prompt, give me a Wikipedia article about the transformer, and the output is this. And it's a pretty believable article. So at this point, it's hard to find much difference with ChatGPT. It basically says that it's, here it decides that transformer is going to be Japanese band. It knows that bands dissolve, some, drummer goes away, and so on. There is something going on. So it actually produces very nice, interesting Wikipedia articles. Anyway, I'll finish with throwing various developments in those days in natural machine translation with another architecture, which is a fancy version of the transformer. This came out in 2020, also by collaboration involving Google Research. So it's called Reformer. So this is the last one, so I'm not going to spend too much time on it. But now, without further ado, let me go back to mathematics, okay? So I started with mathematics. I showed you that untangling knots is somehow interesting question. So here I have my headphones. This is typical picture that I see my headphones, or how they look like. And question is it untangled? Can I fully disentangle it, or is it intrinsically knotted, okay? So that's basically the question that we asked together with Jim Halverson, Fabian Rell, and Piotr here. The project started exactly 5 years ago in 2019, so the paper appeared a bit later, but so by now this is very old stuff. So the reason I decided to talk about it here is first because Piotr is a familiar face to you, and secondly because it's actually among mathematical problems, this is very visual. It's basically trying to, like, child's play, disentangle something. And we already saw that to operate on this tangle strings, you basically need 3 moves, like in Atari games, 3 Riddemeister moves. So we can already anticipate that this should be a fun game, or easy enough game, or interesting game for AI. We'll see how it performs. But there is actually something that we can do even better. So when we try to encode a problem from mathematics into AI game, or train agent to learn it, one of the main things we have to think is what data representation we're going to choose, because that's going to affect performance quite a bit. And then on top of it, we also have to spend a lot of time choosing right algorithm and right architecture, and always it's a good thing to experiment with all 3 components. So here, there is already something that suggests that what I told you about natural machine translation is going to be relevant, because one useful way of representing this knotted strings, like this one, is not really as one-dimensional object or not by picture, but rather by what we call a braid. So the braid is what's shown on the right part of the slide, and it basically is a straightened version of this, where the top and the bottom of the picture are identified. So imagine that I glue top and bottom, so only crossings happen in the middle, and now I can read this as a music score or as a book. And every time I encounter some of these crossings, if they happen between first 2 braids, I put sigma 1. If they happen between, say, 3rd and 4th, I put sigma 3. And now, if I record this information, what I'm going to get, I'll get a string, sigma 1, sigma 3 inverse, sigma 1, and so on and so forth. In fact, mathematicians call this product a braid word. Braid word is already sounds like a word. It already sounds like text. So therefore, what I'm asking is this braid word representing a trivial or non-trivial knot? So now, here I decide not to twist. Let's just identify top and bottom to make it simple. But yeah, we have to make a rule how we identify. But basically, the point is braid word is, on the other hand, a perfect representation of knots. On the other hand, it already sounds like part of language. So therefore, we can take our language models and see, can they understand this language of braid words, right? So that's what we did. And we learned several interesting things. So this is performance as training progressed. So we applied this fancy version of transformer that is called reformer. And we learned that, first of all, it wasn't even needed. So even with a much more basic architecture of, say, feed-forward network, we would actually get really good results already. So it turned out that this knottedness is easy problem for machine. Secondly, we learned that going up to 100 crossings is not a challenge. That's not a problem. And in fact, what we learned, as illustrated here by different lines, that was also a bit of a surprise, that if you give it more complicated knots or braids with more crossings, it actually does better. So this difference between blue, orange, green, and red lines is precisely increasing number of crossings. And the more crossings it sees, it actually plays better. We don't have full explanation for this, but one component could be figuratively that of explanation is that it's like as if you play chess with stronger opponent, you're probably going to learn better. So maybe that's what's going on. But again, we don't know. This is interesting phenomenon to dig in. And yeah, so this is the result that we found. I think we were super happy because, again, this is training, and the scores quickly approach 100%. That means that it does really well. So it sounds like a great success. At least back in the time, I think we all were super excited. So it basically means that machines can do math, as I'll explain in a second, way better than humans. So as human, we cannot go to 100 crossings, and God forbid. But
what happens to these percentages if you go to million epochs?
I don't know. I don't think we waited that long.
But that will not go to 100.
I don't know, but that's something. Yeah. So it already approaches 100% or close enough. That means that statistically we were good. But I think what you're anticipating is something I want to return to. So again, since it's my own work or our work, I'm allowed to criticize it a little bit. So indeed, when we see in machine learning or data science journals, articles which have graphs like this, usually authors say, oh my gosh, this is a great result. But this is not a great result. And I didn't realize this back at the time. I mean, 90% plus is usually considered good, but I think you're anticipating something I'm gonna emphasize in a little bit, where now these days, I actually would love to go back and revisit some of things here. In particular, as the question illustrates, it's interesting to zoom on what happens with that small percentage. It doesn't matter if it's 1% or 0.1% of things that it's not solving, actually. So in other words, the hard cases, okay? So I'll come back to this in a second. And by the way, for anticipating this, you also get a prize. So. I'm not going to throw it. It's hard. Yeah. Yes, there was a question.
What's your performance, like a training score, a test score, a data score? How did you report that?
Right, so we do the usual thing. So in machine learning, of course, what happens is that you train on, say, 80% of data. You keep the val score and the test score, val set and test set, which is usually, I don't know, another 10-10 or however you divide it. So that's how we did it. In fact, here there is, as anticipated by your question, another important concern. I mean, if it was proper data science seminar, I would spend a lot of time explaining how we prepare data sets and what exactly is the training, what exactly is the game. I don't know if that's the direction in which you want to ask. I don't know, follow-up question, or we can, yeah, we can chat. But anyway, for asking the question, you get also a prize, as usual. So let's see. I'll give you this one. So I think I'm running out of prizes. I'm sure you can solve this or train a machine to solve this. Okay. So what I showed you in a previous slide here is actually decision-making process. Here we had this reformer, and again, like I said, you can use actually any architecture. Everything will work. It's an easy problem from knot theory. And we were asking the question to make a prediction, tell us whether you think, after seeing this picture, whether it's knotted or unknotted. And again, accuracy was pretty good, so on. But it wasn't actually doing the unknotting. So that was second experiment, which is shown here. And this is really another branch of machine learning. So the previous one was trying to classify labeled data. So that's a little easier. What's shown here, it belongs to the branch called reinforcement learning. Reinforcement learning is really about playing the game. So that's the one which is most relevant to the title of my talk. And that's actually the one I'm most passionate about these days. So this is reinforcement learning agent. So it's really meant to play the game and not only tell me if it thinks that it's knotted, but really do the moves. I mean, really play the game. And this graph illustrates something else. It illustrates that among different, so here I'll introduce you to a couple of other techniques. So these are different algorithms, and they perform differently. So first thing you can try to do, and this is usually comparison to many of these algorithms, is to just send a random walker. So randomly start sampling, making actions. That's why I distributed dice as my rewards in this lecture. So random walker is the green line or dots, and as you can see, it performs very poorly. So as your braid length, which is number of crossing, increases, it plummets. It basically, it can, of course, in a longer braid, it cannot find how to trivialize it, even if it's completely unknotted. So it's very poor. So there are a couple of algorithms here. The orange is so-called asynchronous advantage actor critic algorithm, and it's actually pretty good. Usually it works well, but here it doesn't. So this illustrates that depending on what problem you're trying to solve, you may try different things, and actually it's a good thing to experiment. And the one which performs really well here is this so-called TRPO. This is Trust Region Policy Optimization. That's a more sophisticated algorithm introduced much later. I believe it's 2017 or so. And what it does is roughly the following. So the way neural net tries to optimize weights or learn how to make the moves for the future games is that it uses under the hood gradient ascent or gradient descent. But imagine that your landscape of rewards or steps is very rigged. So you can make a step in the right direction, but if your step is too big, you can fall and never recover. So this trust region policy optimization, roughly speaking, what it does, it says where you're standing with the current state, it draws a region of a certain radius, and then tries to optimize within that region. So you kind of guarantee that you're not going to fall really bad. But it's also more resource consuming, so it takes longer to train it and to work with it. So that's what roughly is illustrated with these hikes, where gradient ascent or descent is of course, life-threatening, or it can be. So this slide is for my mathematics friends. I ask you to show hands if you're a mathematician. Some of my colleagues could say, well, Sergei, unknotting problem is fun and it's challenging. We don't know how to solve it, but it's not one of the major problems in math. You have a question?
Yes, I have a
Sorry.
question. This slide, I didn't get like, what do you mean by accuracy? Like previous.
This one.
Like the model just have to do like an allowed thing, or like out of time? Because I think if you have like give him infinite time, it will at some point.
Right. So in most of this, yeah. So when you train reinforcement learning model, most of the time you want to do either ask it to win the game in finitely many moves or finite amount of time when you try to compare things, so that we're fixing what the benchmarks are. So I actually don't remember what was fixed here, but yeah, I believe it's a fixed time. Yeah. Because I think I also have a slide which shows number of moves that each different algorithm makes, and for that it would only make sense if it's fixed time. Yeah. So I think, yeah, fixed time. I only have, I think, one prize left, so I'll just give you whatever I have. So sorry. Okay. Right. So fast forward. Yeah, to this slide, so to mention to connection to serious mathematics. So in mathematics, what we serious mathematicians want to do is to solve problems like Riemann hypothesis. Or in topology, which is closer to what I described today, the famous problem that everybody wants to solve is smooth Poincare conjecture in dimension 4. It's very easy to state. It basically asks if what looks like a sphere in 4-dimensional space is actually a sphere. It sounds like an easy question, and the answer should be, I don't know, probably yes, but it's surprisingly non-trivial. And in other dimensions, it's surprisingly easy, or much, much easier, and for many years, we couldn't make much progress in dimension 4. So surprisingly, this question about smooth, exotic structures in 4 dimensions and so on, this Poincare conjecture, that if you solve, or if I solve, we would happily retire, I mean, this is that kind of problem, boils down to a question about knots. In fact, it's a question about knots, which is also a decision problem, yes or no. And I only have to add one more move to play this game, which is called sliceness or ribbonness and so on. And it's surprisingly hard, so basically I just have to modify my game a little bit, and that's going to be now a progress toward, or a way to attack the Poincare conjecture, which is basically like Riemann hypothesis of topology. So what the issue is? The issue is that the problem that we're discussing here, just like board games, the game of Go or the game of chess, they have too many configurations. So this graph shows you how complexity of knots grows as the number of crossing increases, and what do we want and what we could do with traditional computers. So before 2015, I was a quantum topologist, so it means I can try to construct various invariants for knots, and all I could do by hand is really up to 10 crossings. I'm not kidding. Even with help of computers, Mathematica, whatnot, maybe 16 crossings at best. And part of the reason is that, first of all, the number of knots grows very, very fast. Okay? And also, if you're trying to do these operations, the more crossings you also have exponential explosion of possibilities to try. And even if you're computing invariant, you basically, for each crossing, you have to do some sums, they accumulate, so everything basically explodes very, very fast. So that's why, even with computers, something like traditional computers, I mean, without using AI, Beyond 20 crossings is really tough. And regions like 50 crossings or 100 crossings are completely unattainable. On the other hand, for real problems in mathematics, there are lots of interesting counterexamples. For example, to the Poincare conjecture, this big reward that we as mathematicians want to get. But it requires working with 50 crossings at the very least, and ideally with something which is like 100 crossings and more. So here I put pictures of people who proposed counterexamples, and it would be interesting to work with that. So there is a huge gap between what we can do or could do without AI and what we need for real math, serious math problems. So these days, now I'm getting a little closer to conclusion, but I want to leave one more point. There is a lot of interaction between machine learning and mathematics. And yes, you can formulate your math problem as a game. For instance, if the goal is to find a counterexample or example of something famous and we don't know what it is, yes, we can try to set the game and reward system so that we find it. And there are other branches where you can use AI to assist automated, or to automate the proof assistance, such as combine AI with Lean, for example. So this is also something that's happening these days. And I thought that this is a separate story, but it's actually not. So imagine that we're trying to prove Riemann hypothesis. So we have, in all of these problems, we have some starting point, such as statement of the Riemann hypothesis, or assumptions that go into it, and we have the goal, which is the final output. So basically, when we're trying to prove Riemann hypothesis, for example, we need to find a path which consists of logical steps in a proof, and we have to find exactly the right sequence of moves, these logical steps in a proof, so that it takes us from hypothesis to the goal. So in fact, all math problems, I want to argue, are of this type, where you have to go from A to B, from hypothesis to the goal via proof steps, or as I described today in this game involving nodes, going from one instance of our presentation to another instance by, for example, changing crossings and so on. So what's crucial in these sequences or in this type of problems then is what kind of problem we are in. For instance, there is a big difference between two-dimensional labyrinth, which I gave out in a couple of brochures here as rewards, yes, and three-dimensional one. Because in two-dimensional one, we can make moves only in a plane, but in three-dimensional one, complexity increases. So first question we should ask, our math problems, are they more like two-dimensional, three-dimensional, or maybe multi-dimensional? In fact, if you think about Reidemeister moves that I showed you in the beginning, it may sound like our problem that we're discussing is more like three-dimensional because we have 3 Reidemeister moves. So those of you who love math, I offer the following problem. This is a simple Olympiad type problem. So suppose you have to go from upper left to lower right in this grid. Question is, how many non-self-intersecting paths could there be? And to make them non-self-intersecting, we can imagine the following simple game, that the mouse is only allowed to move either to the right or down. Okay, then we guaranteed basically that it's never going to self-intersect itself. So if the size of the square grid is n, so if it's n by n, how many choices of path does it have? N squared, n factorial. So, anyone?
How many non-intersecting paths like n squared?
Yeah, between the start and the finish. Yeah.
Start and finish are done. So here we actually have only 2.
Well, it's quite more. Yeah. Very good. Yeah. What about the cube? It's actually very similar. Yeah, I mean, your thinking is in the right direction. I ran out of prizes, but you're on the right track. So it's not really, oh no, it's actually very similar. So same logic that you gave you to n, choose n, will also give the answer for the cube. Yeah, so the point is, indeed, as these questions illustrate, that the number grows very fast. So it's important to know what kind of problem, math problem, what kind of labyrinth it is, what kind of game we're playing. And here, there is a stark difference between top left and top right, so that you hopefully can see yourself. First thing that can happen is that your labyrinth can be much denser and you can have more obstacles. So that could be an issue. So then there is another thing, that the difference between, for example, top pictures and lower left. So the difference is that in top pictures, I have only one exit point. So I have to find, especially if my labyrinth is very complex and multidimensional, like on the previous slide, my agent have to hit really the right exit, otherwise it will never find something. So in fact, I had a very good question. Do I limit the time or number of steps when I train? And if there is only one point where it can reach a reward, then it will be very, very sparse reward situation. So it will be very, very hard for agent to find it. Whereas for the picture on the lower left, it can actually find exit or get to the cheese in multiple different ways. So that's something that is always good to explore, and this is something that we didn't do in that paper. So that's, I told you that there is something missing, and it would be actually good to look at those examples which were difficult and try to analyze to which category they belong. This is extremely important because this is exactly what distinguishes easy math problem where proof is very straightforward and machine can find the sequence of steps very quickly from problems like Riemann hypothesis, where many people think that the proof exists. But the reason it's hard to find it, or Poincare conjecture, is that these are problems with ultra-sparse rewards where these paths that connect A to B are very rare. And we're in a situation where if agent finds a path, that of course a game changer because now it knows where to go, now it had a reward and it can replicate and improve its performance. But until it finds that, it actually may just randomly keep searching in the dark and not find it. So this is, now I'm becoming actually more serious in terms of machine learning. The actual challenge at the cutting edge is to find this, we call them unicorns or needle in a haystack, depending on cultural background. We can call them black swans. In fact, if you Google black swan, you'll find this interesting fact or theory that's popularized now by Nassim Taleb. So he's Lebanese American economist and author of this book, also called Black Swan. So it's interesting fact that until fairly recently in history of our world, people thought that there are only white swans. And first black swan was discovered fairly late in Australia, and after that, of course, we know that black swans exist. So it basically illustrates and became this kind of footprint of the phenomena where until something is found, we have essentially zero reward. But when something is found, it qualitatively changes the nature of your game. So I want to finish with this point and say that current research in machine learning, and especially in applying it to very challenging problems in mathematics, is more like finding or looking for these unicorns or black swans, because these are problems where rewards are very lumpy and extremely rare. So you have to really search hard, but then once you find it, the story qualitatively changes. So I'm hoping that not only machines will help us to win games such as chess and Go, but in the near future, they'll help us to make truly scientific pioneering discoveries in mathematical sciences and, of course, in other sciences. So thank you for your attention.
Okay, thanks a lot. We have time for a few questions.
I don't know if it's an accurate question, but did the system expand the chess rules, or did it stop on themselves as we know them?
Sorry, can you repeat the question? And which system you are talking about? I mentioned many.
One from the beginning, where the computers tried to replicate the chess rules. Did they expand the rule book, or they were stopped when they reached the...
Yeah, I'm not an expert, so the question, if I understand correctly, is about board games and how computers play the game. So Deep Blue, of course, actually played very differently compared to modern systems, but modern AI systems, which I'm still not expert but know a little bit more about, they learn their own rules, in fact. So they do a lot of self-play. They also play with or read whatever existing tactics and strategies that are available. But curiously, they, via self-play, discover new tactics and strategies which we human actually never thought are possible. So in some of the famous games, that's actually how it happened, that machine learned to make very unexpected things, to sacrifice positions in order to win the game, and that completely threw off the human player.
I have a question about problems of proving mathematical theorems using AI. Because in the history of mathematics, it's in several instances, it happened like that one particular problem somehow generated the whole branch of new mathematics. So that this was this potential of creativity. People invented some new language to describe something and finally solved the new problem. However, this new branch of mathematics was, in a sense, as a legacy, as something that remained. As I understand how the things you were talking about work is that we transform a mathematical problem into the game, and then there is a possibility, I don't know, maybe it is very efficient for finding counterexamples, for example, but for us, an actual tool for solving problems, having in mind this possibility that some new language can be needed, I can't see it. Do you think that the development of AI will be such that it will be possible?
Yeah, like I said, thank you for the good question. I also didn't see it when I joined this, because I thought, okay, how could it be useful to us, because we love this purity and paper and pencil and ideas. How could it generate ideas, basically? But now it can, and that's related to, first of all, the previous question. Did it invent, by playing chess, something that could become now material for the new book, for strategies in game chess? And the answer is yes. It actually invented new strategies that we human didn't think of. And in the last part of my talk, I try to explain that, yes, we don't have that many proofs of Riemann hypothesis yet. We don't have that many data to train it on. So, but from the AI point of view, if it finds a proof, first of all, it can introduce something similar to strategies in a game of chess, so that would be new thing. But in any case, it will be basically thinking outside of the box, because that's what in data science and also in mathematics application of it, we need most. We need to teach computers how to not only replicate things that are similar to what we're doing. That will only replace students, apologies. But if you teach them how to think outside of the box, that will replace experts. That will actually produce new branches, new ways of thinking. And many believe that the answer is yes. So in fact, this question is actually synonymous to developing AGI, artificial general intelligence. So many believe that this is basically around the corner, and I think it's exciting. So at this point, it didn't happen yet, and it may never happen. There is a chance that developments will plateau exactly where we are, and this trajectory will just stop. But then it's also exciting because it means that so many people who are betting on it, Elon Musk, not to mention, just to throw one name, will be wrong. So I think it's very cool. We live in a very exciting time, whether if it does prove Riemann hypothesis in a few years, it's exciting. It will generate new math. If it doesn't, it means so many people, influential people, are wrong, which is also exciting.
I have, frankly speaking, two questions about the paper that you showed about knot. The first question is, you showed the probability of the unfolding the entire knot. So the probability is of unfolding the entire knot from 0 to 100, or just the probability, let's say the probability to what level the unknown will be unfolded. So it will not be entirely unfolded, but we unfold like 98% of it. So this is the first question.
It's the first version. It's
Okay.
a probability of either fully yes or fully no.
Okay, cool. So, and the second question is, you said
Because,
that
sorry, to interject, in part it's hard to measure what exactly we mean by intermediate point. So
okay, cool, thank you. And then the second question, as you said, this problem or unfolding is applicable to different areas in our life, like finding black swan, unicorns, needle in the haystack. And then for the paper, you applied the reformer architecture to solve this problem. And did you think like if it will be valuable to take such events, rare events, like Tudil's Day from our history, we have a lot of them. Maybe not a lot, but and taking them as a training data set and train on this architecture or fine-tune the transformer or reformer-based model and try again unfolding with this new architecture. And what do you think about this?
Well, in my experience, just taking off-the-shelf algorithms and architectures, some of which I shared with you, will not get us to find black swans. So that's related to the previous question. To find black swans and to develop AGI, we need more clever tricks. That's why I left this part for the last. To get 95% on certain problems, or even 99% or 99.9, we can take off-the-shelf algorithms and many things I showed, like reformer. But to me and many other people now in this field, what's most exciting is to get this 0.00 very small subset of problems which are like extreme Winograd schemas, like Riemann hypothesis. And those will require not just off-the-shelf combination of algorithms and architectures, but some much more clever tricks. Again, if I had more time, or if it was a professional seminar, I would start going into that. For instance, one tool that many people try is to, so suppose you want to go from A to B, and you know that you're looking for complicated enough path. So one thing you can try to do as you train, you can actually start changing your action space in a dynamical way. Not just use same 3 moves all the time, but as you train and as you see some of more complicated problems, you can record that, oh, complex problems required me concatenation of moves, which is length 100. Let me take this 100 chunk and add it to the action space. And things like that. So it requires actually developing theoretically new algorithms to play the game. And that's what I find quite exciting. So this is really trying to teach machines how to think outside of the box.
Thank you.
Not with existing things.
Actually, I understand that artificial intelligence can help when we know what the victor is and what the failure is. But if we don't know, for example, if I request, try to formulate quantum theory of gravity. We really don't know what it is, what is the path towards, on what subjects, on what examples I should teach that it is a good move or it is a bad move. It is a dead alley and it is something that we should follow. I have nothing to propose to teach this, that what it should do, because probably we should change both quantum mechanics and gravity to arrive at it. So then we are completely hopeless with the artificial intelligence because we don't even know what to say. Yes, it is a proper path towards quantum gravity or not. For example, string theory. I spent 17 years on string theory and turned out to be a failure in explaining the real world. So it looked very nice, but there are no examples then. If we have what is victory in chess, in Go, in whatever, or here, for example, your artificial intelligence could prove that the Poincaré conjecture is equivalent to this knot. That's a problem, and not proving the counterexamples. So that's something that we don't know, that even going in the direction of knots could be equivalent to the original problem. So that's the problem that I see. The real creativeness comes from seeing or going in the direction that is not obviously right, like going from Newton's gravity to Einstein's gravity. It's completely different. It's using different language, different concepts. So that's where the human being will still be needed. That's my statement.
Thank you for question and comment. I don't disagree with you. I think that's very true, and again, it's related to other questions. So just like it already demonstrated in board games and in other simple games, it can invent things. Question is, do we consider these inventions interesting enough steps on a linear trajectory that's going up? And if the answer is yes, if it proves Riemann hypothesis, again, I'm sure it will invent along the way new tactics for that we haven't thought about, and that's very cool. So that's why myself, I'm limiting my study to world of mathematics, which is slightly more rigorous, and in particular, it's more verifiable. So if it gives me a proof of either proof or disproof of Poincare conjecture or Riemann hypothesis, we mathematicians can sit down and check. If it's reinforcement learning giving me the steps, we can just follow the steps and say, yes, that's correct. Or Lean will verify it for us. But applying it to other areas, especially where we are more in the dark, is potentially dangerous. So that's, I think, kind of discussion that we hear in the media. What happens if, say, AGI arrives today and we don't even know how to judge its actions? So for that, I have no comment.
Well, okay. I don't see more questions, and one of the conclusions is that we don't know, as far as I understand. So maybe that's a good moment to thank the speaker. And see you next time, which is not quite specified yet, but it will be announced in our website as usual. Thank you.